like to introduce Brian Jones from Colorado State University. Really looking forward to his talk on a warm planet in a cold universe. It's about making climate change concepts accessible and acceptable to a wide audience. He's got a lot in store for us, so I'll go ahead and start you here.
The countdown begins. Awesome. It's kind of ominous. I have this like countdown clock and like buttons that turn from green to red. So I hope something really bad doesn't happen if I go over. So I want to thank Kevin for asking me to be part of this session. I want to thank APS for giving me the opportunity to do some advocacy, basically, because that's my intent today, is not just to tell you the kinds of things that I've been up to and the kinds of things that you could do, but to convince you that you should. The title of this session is Attracting Young People to Science and Science Policy. And I would say the best way to attract young people these days to science is through science policy. That's my feeling as I've gotten to know the young people that I work with. So I'm going to talk to you about the specific topic of climate change in this context. And first I want to give some introductions to who I am. I do this program called Little Shop of Physics. Ooh, and I got a little red arrow here. So there's me. Well, awesome. I'm going to move this out of the way. I do this program called Little Shop of Physics, and it's a science outreach program at Colorado State University. I've been doing this since before my students were born. I've been doing this going on 30 years now. And I get to travel all over the world to do this. And this was a session I did in Norway. And actually, it was really, really interesting because I did a session in Norway called A Warm Planet in a Cold Universe, which is the same title I use for every single talk I give on this topic. And it went over really, really differently in Norway than it does in the United States. It was really kind of an interesting thing to be there. But I get a chance to work with teachers and students all over the world, and the idea is to engage them in science and the process of science and the wonder of science. And we're particularly trying to work with like young people and get them engaged this way. The messages that we learn, they'll carry over into my day job. And if you ask my department chair what I do, he wouldn't say, oh, Brian does Little Shop of Physics. He'd say, Brian's the person who teaches 25% of the department's credit hours. I'm a huge cash cow for the department because I teach the Stack 'em Deep and Teach 'em Cheap courses. And so I teach a lot of young people, but I really appreciate the opportunity to be able to work with so many young people. And my goal in my day job is to try to engage the young people in the same way as I engage the people that we work with all over the world through the Little Shop of Physics program, to teach them the wonder of science and the process of science. Some of the materials I'm going to talk about today, I have this page here. We made a climate change kit for the local Poudre School District at Colorado, up in Fort Collins, Colorado. And all the materials that I'm going to talk about are presented here. And there's a whole page, and it's just available to whoever. You won't have the equipment that we shared with the Poudre School District, but you can definitely download all the different documents. So I first want to mention, as I say, I'm going to be doing an advocacy talk today in some sense. I want to convince you not only that you can do this and give you some ideas about how you could talk about climate change and talk about other social policy issues in your classes, but it's okay to do this. And I was really worried, kind of like in this era, which is very politically polarized, like, would it be okay to talk in my classes about something which these days, even though it's a scientific topic, it comes across as being political. And the answer, is it okay to do this? The answer is yes, it's fine to do this. And I haven't gotten pushback. I got more pushback 5 years ago. But these days I'm not. And it seems to me that the young people are kind of like hungry for this sort of thing. So when I talk about climate change, I do this once a semester. I devote a whole day once a semester to climate change. And I can do this as a physics lesson because there's a lot of physics involved in the way the climate works. So I'm teaching physics, but I'm doing it through this lens, and it's fine. And the students seem to actually appreciate it. And that's my first step to suggest, because I want you to do this. I'm going to give you some steps that I suggest to make it possible. One is to just know your audience. And one of the things I know about my students, and I would suspect if you're teaching the current generation of college students that the same is true for you, is that they're really, really worried about the future. They're deeply concerned for the fate of the planet. And so one of the things I do with my class as part of when I talk about climate change, and I'll do this on Monday, actually, I'm talking about climate change in my class, I'll say, just tell me what's one thing that worries you the most when you think about the future of the planet. And I ask them to write it down on the tables because we have these whiteboard tabletops. And I'll walk around the room, and I would say a quarter of my students are writing down climate change. So it's like, well, that was easy. A quarter of you are already concerned about this. And most of the messages that I get are kind of like related things. They're worried about environmental catastrophes. They're worried about diseases. They're worried about resource depletion. And so they're really deeply concerned about these topics, and giving them the chance immediately to kind of say, tell me what you're worried about, really kind of like opens them up to thinking this way. I also will say, if you're going to talk about this kind of like topics which can be kind of doom and gloom, I would start with a hopeful message. And I always do this, and I say like, oh yeah, when I was a little kid, my mom taught me about the bomb. She taught me when I was 8 and told me about kind of like nuclear weapons. And it was a heavy message to lay on an 8-year-old, but she just wanted me to know that I was living under the threat of complete nuclear annihilation, and might as well get that out of the way. We're having a talk about where babies come from. That's disturbing. Let's do this one too. Let's just get it all on the table. It was all good. And so I could tell my students, like, I grew up like, when I was 8, I didn't think I would live to see 9. And then when I went to college, and I learned about kind of like the intricacies of how nuclear weapons work and also nuclear policy, I didn't think I would live to see 21 for sure. But I did, and it was kind of awesome. So I just let them know, we've had big problems before as a species, and we've solved them. And then also, too, if you're going to talk about this, something that's political, just acknowledge this. And I just acknowledge it right up front and say, like, climate change, this is a political issue these days. But everything that we're going to talk about is not political. We're talking about science. It's a physics class. And I don't take an advocacy role in the class. I don't want them to know that. I'm just going to talk about physics. But putting this out there, saying like, I know it seems political, but today we're just talking physics. Getting it right out there seems to really help. And then after that, I just absolutely stick to the physics. So I'm going to show you some slides that I use with my class. And one of the things that I've tried to do with this, and I do this with my class, but I also do this in the public presentations that I do, I try to simplify my story. I want to give one message that people can take home. And the message that I give is that carbon dioxide helps keep the earth warm. And we're just in a situation now where perhaps we have too much of a good thing. So I'm gonna stick to that, the whole story of thermal radiation. So I refer back to things that my students have talked about, and I want to show them things that will stick with them. So I talk about absorption and transmission and different frequencies and resonances and things like that. And I say, okay, you're familiar with this in other ways. When you wear sunscreen, the molecules in sunscreen absorb ultraviolet light, and they're just tuned to that resonance in some sense. And so molecules and atoms have particular frequencies they like to vibrate at. You don't think about sunscreen as looking like black paint, but when bees look at you, because they can see ultraviolet light, they're just laughing their little bee heads off because you look like you're putting black paint on your face. And I kind of like let them know about that. It's transparent in the ranges that we see, but it's opaque in other ranges. And the atmosphere works like that too. That's an important piece of the puzzle. Now, it's also true that the waves that are passing through the atmosphere carry energy, and particularly the thermal radiation is going to be an important part of the story I want to tell. And radiation is something which we talked about, and we talk about extensively when we talk about thermal properties of matter. And I remind them the details of this, that if you're talking about thermal radiation, emission and absorption is basically the same physics. If you absorb, you emit, and the emission frequency is proportional to temperature, and this is all stuff that we know about, and I go over some of the frequencies. And then ask them this question, and I want to warm up with a question that's pretty easy for them to get, which is hotter the sun or the earth. They're pretty confident about that one. And then it says something about the relative frequencies of the emission. And the earth emits at about 10,000 nanometers. The sun emits at about 500 nanometers in round figures. And so the physics of the interaction of that radiation with the atmosphere, with the environment, is extremely different. Now, we know this. The Earth warms by absorbing visible light, and it cools by emitting thermal radiation. And I make a big point about talking about this when I talk about heat transfer modes and say, look, the Earth sits in a vacuum. There's no conduction, there's no convection. The only way we can get or emit energy is by radiation. So all the energy that comes in that warms up the Earth, it's mostly in the form of visible lights. But we emit energy as well, and it's in the form of this thermal radiation. And here's a picture of the Earth from space, and it's a thermal image. And you can see we're emitting a fair amount of thermal radiation. It's also interesting to look at the patterns of where it comes from. And if I have time, I talk to my students a little bit about that. Like, you would see kind of like apparently hot places here that seem chilly. I get a lot of blues going on here. Why is that? That's a piece we can come back to. Now here's the next thing I ask my students to think about, and this comes as a surprise to them. Over the course of the year, the average temperature of the Earth is approximately constant. So what does this tell you about the magnitude of the energy absorbed and emitted by the Earth? And the answer is they're approximately the same. And this really blows my students' mind. And I want to give them single points that stick in their mind, like this blows my mind, and this is going to stick in my mind, and I will take this with me. And here's the way I phrase it to them. The Earth is shining as brightly as the sun. And this is true. We absorb radiant energy and we emit radiant energy, and the magnitudes of those two are the same. So, as physicists, you might doubt the exact way that I phrased this, but this is very sticky for my students. We're giving off as much energy as we are absorbing. The Earth is shining as brightly as the sun. That's quite a compelling point because they've never particularly thought about that. And this makes a difference on small scales. And in Colorado, we know that it works this way. It doesn't snow because it's cold. It's cold because it snows. And this is something that I tell my students about. I say, watch this. It's going to snow, and the next day it's going to be cold. And the reason is because when the sunlight comes in, the snow reflects it back to space, so you don't get the warming. But snow is a really good emitter of thermal radiation because it's made out of water, and water radiates like nobody's business. So you lose the absorption, and you ramp up the emission. And so as a consequence, it gets cold when it snows. And if you live in Colorado, if you haven't noticed this, watch for it. It snows, and then the temperature drops. And other places, it's kind of more complicated, but Colorado, our weather is very variable, but in some ways really, really simple. And I remind them of the reason why water interacts with electromagnetic waves is because you've got this huge dipole moment. You've got the separated charges. Nitrogen and oxygen don't, but the greenhouse gases do. And the resonant frequencies basically mean they absorb and emit thermal radiation, but not the visible light. And I have a graph they share about that. But I want to make it compelling with an image. And here's one way to look at it. This is a picture of the Earth taken from space, and this is by the GOES satellite at a wavelength of 12 microns. And if you take a picture at 7 microns at the same time, it's extremely different. And so you can look at the absorption and the transmission, and this is very much like the picture of the person putting on the sunscreen. You're not seeing emission from the surface of the Earth. If you look here, I'm seeing a lot of emission here from the Atacama Desert on the west coast of South America. But if I look here, I do not see this. At this wavelength, the atmosphere is largely transparent. So if we were invaded by aliens who had 7-micron vision, they would say, oh, it's cloudy, nothing of interest to look here. Let's move on. It basically looks like Venus. Crazy thing. Now, here's the thing I remind students. Absorption and emission is the same thing. So if it's absorbing the electromagnetic waves, and it is because we know that it is, it's also emitting, and so as a consequence, the sky is shining on you. And here's a kind of a remarkable fact. Over the course of the day, the Earth receives more radiated thermal energy from the atmosphere than it does from the sun. So if you're warm, don't blame the sunlight. Blame the sky shine. Basically blame the fact that the atmosphere is radiating energy on you. And it's kind of a really remarkable fact. And this, again, sticks in people's minds and helps soften them up for the idea that since this is such a big deal, if we were to tweak the radiation, well, heavens to Betsy, that might be a thing. And the sky shines 24/7. The sun only shines during the day. And so this is kind of a remarkable thing. And this is the source of the greenhouse effect. The Earth radiates energy, it's absorbed by the atmosphere, and it's re-radiated in this downwelling thermal radiation that makes the Earth relatively warmer than it would be otherwise. If there was no atmosphere, the average temperature of the Earth's surface is negative 18 degrees Celsius. The Earth is a frozen ice ball, no life. And it's a very, very different story. It's actually, the average temperature is more like 15 degrees Celsius, and it's this balmy, wonderful, warm planet in the cold universe that we've come to know and love. And carbon dioxide is a key player in this story, and it absorbs and emits thermal radiation. And one of the things we've done in the Little Shop of Physics is we've made some videos that kind of like demonstrate this. And here's one that's about greenhouse gases. And we put out this series of videos called Show Me Some Science. Here's hot air. And I feel really bad because we just asked this student, just like, we grabbed her out of the hallway and said, like, can we use you in a video? Here's water vapor, difluoroethane. And if you look at it in the thermal camera, it's a very strong absorber and emitter of thermal radiation. So when I pour this, it actually blocks the view of me. It's a very strong absorber and emitter of that thermal radiation. So is carbon dioxide, and so is water vapor. And so I can see the combustion gases from the candle or from the torch, dramatically different. And I got in big trouble for filming a city bus, and it took a long time to get out of trouble, but this worked out okay. And then if we look at this power plant on campus, and this image in particular is extremely compelling because in the stack of this power plant, they've got a thing which condenses the water vapor. Because you get more energy if you can condense that water vapor. So to make it more efficient, they do that. So as a consequence, 100% of what we were seeing in that image was the carbon dioxide. And I show this to my students and say, look, you can see it in the thermal camera. It is emitting thermal radiation. And guess what? When it goes up in the sky, it's going to continue emitting thermal radiation forever until it's like not in the atmosphere anymore. It's going to continue to be part of the story of the thermal radiation in the environment. And it's a really, really big deal. And that video has been really, really compelling. And we have that video and others that we can show people. Having made those stories, or having made those points clear and connected with the physics that the students are learning, you can circle back and say, okay, here's the story. Carbon dioxide helps keep the Earth warm. Carbon dioxide is good, but you can have too much of a good thing. And I like to present it this way, not that carbon dioxide is evil. Carbon dioxide is good. I mean, if it wasn't for carbon dioxide in the atmosphere, we would live on a frozen ice ball. But we just right now might be in a situation of having too much of a good thing. And the carbon dioxide in the atmosphere is increasing. And we know that this is true. And there's just direct measurements of it. And this is incontrovertible, is that the carbon dioxide is absolutely going up. And this is an old video because it only goes up to 392 parts per million, and we're way past that at this point, so I'm going to have to refresh that slide. And it's also true that the increase in carbon dioxide is due to human activities. And you could argue how much of it is due to one source or another, but it's not volcanoes and it's not any other source like that. The extra carbon dioxide in the atmosphere is there because we put it there, and I think it's, I can tell students that tomorrow when I talk about it, I'm going to make a connection with nuclear physics and see how can we say this by talking about stable isotopes, and that is a case that you can make. But here's the interesting thing, and I like to come back to this piece right here. The radiative properties of the Earth's atmosphere are different. We have changed the emissivity of the atmosphere by adding more carbon dioxide to it. So it's not like the reason I believe that the Earth's climate is changing is not because of computer models. It's because carbon dioxide absorbs and emits thermal radiation. There's more carbon dioxide in the atmosphere because we put it there. And you can see by the emission of the atmosphere, the radiative properties are different than they used to be. So we have made a measurable change in the Earth's atmosphere, which is kind of a crazy thing. And then also, after this, I want to make it personal to the students and say, like, you might not think this is a big deal, but over the course of the year, I drive my car not very many miles, but I burn 120 gallons of gas, which is not that much for most people's scale. That emits 2,400 pounds of CO2. That's the weight of the car. My car emits its weight in carbon dioxide every year, and that's a lot of CO2 because when you burn carbon, you pick up a couple of oxygens from the air. And so that's a surprising fact. And this helps people see the scale of the problem. Now, the other way I like to nail this down is to use really compelling demonstrations for how this works, because after we've talked about this in class, I have my students do some things in the laboratory. And here's one that I just love. This is a box that during the day is a solar oven, but at night it's a solar refrigerator. Or as I call it, the space refrigerator. Because if you take this thing and put it outside, it's emitting thermal radiation, and I have plastic on the top that transmits thermal radiation. So it's emitting thermal radiation up to space, and it's not getting much back. Because in Colorado, we have this kind of like high, dry climate, and so it's emitting thermal radiation, not getting as much back. It cools off colder than the ambient temperature. And we have a pair of these that we take out when we do public presentations that have different lids. And one of them absorbs thermal radiation, and one of them transmits it. And the one that absorbs thermal radiation gets all the visible light, comes in, absorbs it, re-emits it. It works like the atmosphere with enhanced greenhouse effect. And the other one doesn't. And you can see a 10 degrees Celsius difference between the two containers just by the type of plastic we used in the lid, which is crazy. To demonstrate the principles of thermal radiation and how important it is, we give students this thing as kind of an interesting experiment. Oh, I have 2 cylinders of aluminum. One of them's painted, one of them's bare. Put them on a hot plate, get them warmed up to the same temperature, let them cool off. Which cools off faster? The painted one, because it's got an emissivity of about 0.95, whereas the metal one has an emissivity of about 0.6. And so the painted one just radiates a lot more. And this blows students away, and it demonstrates the importance of radiation in an energy balance. We have this one here where you use a stack of glass plates. We shine light on it, and the visible light goes through the top plate all the way to the bottom plate, which is black, heats it up, and then you have a series of plates on top of that are subsequently, the energy is transferred, like energy is transferred through layers in the atmosphere. It's like an atmosphere model. That one is a really, really fun one to share. So I've talked about this. I've given them the basic physics principles. I do some compelling demonstrations and let them see these things. And you can see the importance of radiation in these smaller scale things. I'm asking you to accept that it changes the climate. Let's prove that it's at work on a smaller scale. And then finally, I want to finish, and I would encourage people to do this, to make this advocacy role. The students, as a rule, are concerned for the fate of the planet. And they're hungry for people to take these sort of positions. So make that case for the scientific basis. And I'm going to put this slide up tomorrow. Just the carbon dioxide we have added to the atmosphere and continue to add is changing the climate. This will significantly alter weather patterns and adversely affect life on this planet. And there is no serious debate about this in the scientific community. And I work a lot with atmospheric scientists, and I've asked them, if I put this slide up, is that legit? Can you say that that's true? There's questions around the edges and the scope of things and the mechanisms of stuff. But there is no serious debate that the carbon dioxide we are adding to the atmosphere is making an effect on the climate. And then I put this up too, and I say, like, if someone doubts this, either they don't have the whole story or they have an agenda. And you can give them a choice. You can give them a choice. Which one is it? Are you uninformed, or do you have an agenda that you're trying to peddle? And I've been doing this for 5 years, and no one's gotten mad at me yet, which is really, really cool. But if you've done this gloom and doom thing and you put this message out there, I used to stop here, and then I ask students, like, what did you think about that? And they said, we think we're going to die. And I thought, well, that's not necessarily the message I want to leave you with. Sure, you are going to die, but probably not soon. I mean, it's going to happen to all of us eventually. But I want to finish with some sort of a message of hope. And this is really, really important. And I'll share you a couple of things that have really worked well for me. Because if you talk about this and you just finish with that gloom and doom and like, oh my gosh, we're destroying the planet and we're all going to die, that is not a recipe for convincing people to take constructive action. So I give people good news. And I say, look, if we want to fix this problem, we know what the problem is, and we know what the options are for fixing it. We just have to put less carbon in the atmosphere. And this has been a really important piece of the story to tell, particularly for my students who are more politically conservative. And I say, Americans are really clever and enterprising people. We are. And if there's a big problem that has to be solved, doggone it, I want the Americans on the case because we're clever, we're good at this stuff, we've solved all kinds of big problems. And saying this has gone a long way to really dent criticism from certain people. And this has been kind of a really interesting piece. I didn't anticipate that was such a big thing, but to say like, okay, we got this big problem with the climate. Are we going to solve this? Are we going to let the Chinese solve it? No, we're going to do this as Americans. And actually that has worked really, really well. And finally, to convince them that individuals can make a difference. Our problems that we experience as a species are a result of collective choices we have made as individuals. And so the individual choices that they make can make a big difference. And I finish with the story of the ozone hole. And this is something that, folks are familiar with. We had this big increase in the area of the ozone hole. And people kind of like worked out what the science was, why it was getting bigger, and worked out what would need to happen as a public policy thing in order to change that, in order to keep that from being such a big problem. And subsequently, the ozone hole has gotten smaller. It's getting bigger again, but that's a whole nother thing. We don't have to talk about that. We're finishing with a message of hope here. So, and then too, I remind the students, and this has been a really interesting thing to be able to talk to my students about. One of the things I've started to do in my class that has been really helpful is once a week, I tell them, here's something I like about your generation. Because my students have told me we're accustomed to hearing about how we're slackers and we live in our parents' basement and we can't adult properly and we're just not interested in doing anything except for Instagramming our friends or whatever you call that. But anyway, I tell them, here's things I like about you. And this is something I hear from my students a lot. A lot of them say, there's problems in the world, and doggone it, I'm going to fix them. I want to change the world. I hear this a lot from my students. I think that's a really, really important thing. And I remind them, this gives me hope. This gives me hope. When I think about kind of like all the ways that the world could go, the fact that they're the generation which is in charge, I think really gives me hope. And then the last piece of the puzzle is, I would say, finish with the message of hope, and then say, as your homework, think about something you could do. What could you do right now? Not just be hopeful, but do something. And then I give them an example. I say, like, here's things that contribute 1 pound of carbon dioxide to the atmosphere. Okay? It corresponds to all these different things. So think about one thing you could not do. What's one change you could make that would reduce the carbon dioxide you put in the atmosphere? Or what's one change we could make as a society? And giving them that as their homework. I've told you why you can feel hopeful. Now I want you to go do something. It's actually really helpful. And doing a little something can help inspire people to future action. And so my hope is that I've been able to inspire you folks to future action. I have resources to help with this. We've got all the materials on that PSD Kit site, the Little Shop of Physics that I do, lsop.collegestate.edu. We have a little page called Warm Planet where we have some resources collected. Also, we have this YouTube channel. If you go to YouTube, Little Shop of Physics, we have this playlist called Show Me Some Science where we have little videos, and the ones that I showed are in there, as well as videos on all kinds of different topics. And they're free for folks to use. We want people to use them. And, there's going to be tie-dye clad people running around in them, so you don't have to give us credit because the credit's kind of baked in. But I hope that I can encourage people to do this, to incorporate some of this stuff and take this advocacy role. And here's some lessons that I've learned for how to do that most effectively. I got time for a couple questions, I think.
Good time.
Cool.
Let's thank our speaker.
Yeah.
Quick question. I came in a little bit late, but is this class you teach for science-oriented students, or is this a general science requirement?
Oh, no, it's for science-oriented students. Most of the students are in the life sciences.
So how do you attract non-scientists to hear this message? People who aren't oriented towards it.
How do you attract non-scientists? That's a really... when I've done public things, I've actually had better luck attracting kind of like non-science people, because non-science people are more worried about this. They hear about it, but they want to know kind of like what's the story, and they want to hear from someone who knows something about science. So I've had pretty good luck, and I think the social justice and the kind of like public policy angle for things has been really, really good for me to be able to attract folks. Like if I give a talk on campus and I give it this sort of spin, the room is packed. If I just say, hey, here's a talk on why physics is awesome, it's like, meh, I will get some folks, but not as much.
We do it in Astro 101, the exact same thing, and it works great. Yeah, that's
Awesome. Yeah.
I also came a little late. You seem to have a very reassuring voice. Is that something that you find, I would find it effective, but if someone does not have that, is that a necessity to have?
I don't think it's a necessity. One of the things I talk about when I talk with future teachers is develop your teaching persona. And I think mine is I'm trying for kind of avuncular, accessible, kind of like reassuring individual. And I've really worked on that. Yours might be different. You might decide I'm going to go with kind of like learned, expert. And I'm going to speak from that position. And I think work with what you got and think about how to tailor your message to your particular strength. But I don't think you don't have to do it the way I do it. That would be bad.
I might sound very fake.
Yeah, and it's sounding fake, man, they will spot it a million miles away. And that's something that students these days are really good at. Yeah.
So, two things. One, I've been teaching a course on global warming for non-scientists for about 4 or 5 years. We get students because some departments require, like psychology, require their students to take one physics course of any kind they want. And if you have this as a title of a physics course, it's pretty good at attracting people. And in my experience, I have these students come in who are afraid of math, and by the end of a 1/4 course, they can take a model with 3 levels of the atmosphere with different emissivities and different lapse rates and calculate the average temperature of the Earth. So partly I want to encourage that this really.
So you're saying it's a hook. This is a way to kind of like bring people in. If you're worried about how do you engage those non-scientists, this will do it.
I had a request though. Could you go back to the last slide so I can finish?
Oh yeah, sorry. Yep, sorry.
Well, I mean, adding on to that, I mean, most of the people here probably know about like the Physics for Future Presidents course from, the guy at Berkeley, and we've been teaching this at George Washington University. So climate is one of the big units of that. The course that I teach, I have sort of 3 units: energy and nuclear stuff, because I have to do that because I'm a nuclear physicist, which is energy and weapons, and climate. And so you could, of course, have a course on climate, an entire course. I only get a third. But, I managed to connect all these 3 pillars, right? Because energy relates to climate. And so that would be a hook. And that's a very sexy title for a course that could attract and is intended to attract the non-science majors.
Awesome. Yeah.
I do a demonstration similar to the video where the woman's putting sunblock on her face. And I'm a little puzzled as to what's going on, I have to admit. I take an ordinary fluorescent black light, like for a party, and I put sunblock on my hand, and it looks like beautiful purple finger paint. But then, so I tell students, the sunblock molecules don't know this is an extreme violet photon versus an ultraviolet photon. But the fact that it's brilliant purple suggests that it's working by reflection instead of absorption. And so I don't know, honestly.
Oh, there's a couple different brands of sunscreen, and some of them work by reflection, and some of them look like you're putting on chrome paint, and some of them look like you're putting on black paint. I think the black is just cooler for the video. But you must be having something which does work by reflection.
I imagine so, yeah.
It's awesome. I think it's about.
One more question.
So just in practice, is the general physics course settings that you teach this, how much instructional time would you say it usually takes to do this to your satisfaction? Is it like 3 lectures or?
I've built the basis for it in previous lectures because we're talking about the content. I do this as a capstone. So tomorrow, or Monday, I'm going to talk about this in class. And saying, like, we've talked about nuclear physics, we've talked about isotopes, we've talked about radiation, all these things in this unit. I'm going to use this as a way of reviewing all the topic that we've seen. So I devote one day to it because we've built the foundation. If I had to do it from scratch, yeah, it would take a while.
All right, well, let's thank our speaker again.
Thank you.